Thank you for the introduction. Can you hear me? Okay, fine. So I'll talk about automatic understanding of the visual world today. So I'm working mainly in computer vision, but also recently I've moved a bit to robotics. And okay, so computer vision today has made a lot of progress over the past 10 years. There are really now applications which start to work. Probably all available. You have face detectors in your cameras. You can use that for auto zoom. You can recognize landmarks. But things which you cannot do today is, for example, if you have a movie and you want to really say who is doing what and what are the intentions in the movie, it's still hard to predict what they are. So basically here you would want to say exactly, so this is what people would annotate manually. As the head waiter talks them to the table, they pass by the piano, the woman looks at Sam, and so forth. And so this is something which even with state-of-the-art techniques we cannot do. So what people can do today is they have simple classifiers which work well for relatively simple tasks. But if you want to move to the next level understanding, you need to develop more sophisticated methods. And so what are the ingredients of today's machine visual perception? You have obviously machine learning. That's things which we have seen over the whole day. Then what is very important is the data. So I mean, basically, if you don't have the right data, you cannot do it. And then basically this is true for all different domains. And then basically what's also important is obviously to design appropriate models for the task of visual understanding. So not just train up some model, but you need to see what are the dependencies, how do you model the dependencies, and that's something which as of today people still hand code in the model. Okay, and today I'll give an overview over 3 recent topics which I've been working on. So actually the data, what kind of data they want to use. There's manual data, there's synthetic data, and then also people are more and more moving towards weakly supervised approaches. Then the second thing which I've been working on is video understanding, so predict what kind of type of actions are in the video. And then very recently have moved to robotics, so basically now that vision starts to work, my idea was it's actually time to revisit the problem of robotics. Can we really move around a robot in the visual world by understanding what's going on and building models online? Okay, so annotated data. So there's loads of manually annotated data. There's, for example, the open image data set where you have many bounding boxes for 600 categories. I have recently been working on the AVA data set, which is atomic visual actions. So again, we have a lot of annotated data. But beside this, if you look more in detail what's going on there, there's still not enough data. There's many items in the vocabulary which are not addressed. Even if you have 600 categories, it's not enough. You can have new concepts coming on all the time. And then many concepts are difficult to annotate. So if you want to annotate, for example, flow or 3D body shape, then you cannot do it, right? So for example, in the case of 3D body shape, so what we have been doing, basically if you want to reconstruct 3D bodies, you need some training data, right? And if you have real bodies, you have to annotate them, and that's really hard, you cannot do it. So here, the idea is to go towards synthetic data. And so we have, this is joint work with the Max Planck Institute, and we have actually this real human bodies, which we have measured in some setting, setting where you can really measure the precise shape. And then what you can do is you can take some mocap data, so you can have people running around measuring the mocap data, and you combine this together with animations by changing the light, by changing the camera, and changing the background. And then you have this data, which you can create many variabilities. And for this data, you have the 3D pose, you have the part segmentation, the depth, the normals, and the flow. So you have all the annotations, and you can really then train from this data. So here are just a few examples. So despite the fact that it's not completely real, you can see that the quality of the humans is very good. For now, they're still on images, inserted on images. We're currently working on inserting them in 3D real scenes. But then basically you can really see this gives you an excellent corpus of training data, and you can then use this, for example, to estimate the human body shapes in videos, right? And so what we do here, the idea is we have this synthetic training data from which we can go from the input image to the 3D shape. And in order to have some information from the 2D images, what we do here is we have also data which comes in here for the sub-problems which comes from real data. So we have this clever way of combining the 3D synthetic data with some 2D losses here based on the pose and the segmentation. And so we train up this network jointly by inferring the shape and having these intermediate representations. And this way we can actually develop models which we can then apply on real images and obtain good 3D human body shape estimation. And so basically there are many works going on in synthetic data, and one of the problems is still how to make it as real as possible, right? Basically the thing is, the more real you make it, the better is the estimation of the model. And you can really show that before, when people used very simple human body models, it didn't work well, but now basically that we have these sophisticated models, you can improve the quality. So I think this is one way of going away from this manual annotation, is to create better and better synthetic data to have the whole variability and create new concepts. And then the other way to go away from the manual data is to have the weakly supervised approach. And so weakly supervised is basically you have maybe one high-level label. So here it's some recent work for action localization. You have a label which says in this clip you have one action which is performed. And then what you want to do is to learn descriptors for these actions and be able to use them elsewhere, right? So basically the idea of weak supervision is you have some kind of annotations, be it text, be it metadata, be it user-click data. And what you want to do with this then is to use this data to learn the representation, right? And so here, what we have, different levels of annotations. We have the information that the action is performed in the video. You can see you can have an annotation that one frame inside the action is annotated. You can have just a temporal interval given, or you can have the temporal interval and a human bounding box. And so here, what's new here is basically that we take an approach based on discriminative clustering, which combines different levels of annotation. So you can have different ways of annotating each video. You can combine that and then train the action classifier from there. And so here, briefly, what's the approach? You have human tracklets, so you track humans over the video. The tracks are decomposed in very short sequences, so of 10 frames. And then each of these short segments is characterized by 3D convolutions. You have features which describe what's happening inside this tracklet. So here, basically, it's the spatial temporal measure which describes it. And then the approach is based on this discriminative clustering, where you want to assign a label to each of these chunks. So you have these different chunks of tracklets, and you want to assign to which class this tracklet belongs, right? So in the beginning, you don't know. All you have you have an indication about the constraints. So you know, for example, that one of the tracklets should have this label which is given to the whole video clip. So this is the set of constraints. And then what you do is you change these assignments over this label matrix and learn jointly a classifier and minimize jointly over this, right? So you basically learn the classifier, reevaluate, and reperform the discriminative clustering. And then actually what we found what was very important, so these approaches have been around for a while, and what makes them really work is the quality of the tracks and the feature representation, right? So you can have many of these machine learning approaches, but what's really important is actually the data which you give into. I mean, the machine learning gives you a small improvement, and what gives you the largest improvement is actually the quality of the tracks. So we experimented with different tracking methods, and you can really show if you have high quality features and high quality tracks, you can really improve the performance, right? So that's kind of something which people do more and more when they do weakly supervised learning. They combine approaches for which they have data. So for example, here they have data annotated for humans. You use that as an initial starting point for your weak supervision, but then you can mine more information from there. Or for example, people use logo detectors and then use this information to mine more information. And then here, just very briefly, a few results. So basically here you can see that here you can see with full supervision, and then you can see how the performance degrades when you go down with the level of annotation. And what's interesting to see here is that with relatively weak forms of annotation, you can get still very good results. And basically here, what's really important is, I won't go into the detail, but it's really important to have good quality annotations. Okay, and then so basically this was the first part on what kind of data to use. So basically what the field is moving to is to more and more flexible ways of creating this data, because basically, sure, if you're in a company, you can annotate all the data, but at some point you're getting to the limit, right? You cannot annotate every and each concept in the world, and in particular, if you look at actions, there's so many variabilities and variants of actions that you cannot just sit there and annotate and define the vocabulary. And then the second part of my talk is on video understanding. So here, why do you want to do this? Obviously, what you want to do is not just classify the content of the video, but you want to see also at which moment in time the person is performing which action. So here, for example, you want to predict that the person is walking, but you want to also predict in which direction it's walking, and that you know here that the person will be crossing, for example, the street, and you have to stop the car. Or in video surveillance, again, you want to see what all the people are doing, and if there's some kind of action which is suspicious, for example, somebody putting down some suspicious object, then you want to create an alert. So here you have to really go into the details, understand where the people are and what kind of actions they're performing at which moment in time. And so here, one application would be, for example, next generation home assistants. So you want to have an assistant with a camera, and you want to observe what's going on. And so tell the person, for example, your son is forgetting your school bag. You can see that basically he's walking out of the home. You understand the context. Or you can look at somebody cooking, and you give them guidelines that you forgot to put in the spices in your dish. Or you can say, now you need to do this and that. And so here again, you need to really understand what's the action and the context and how it interferes with the scene. And then so more like just from a schematic way. So what you have here, so you have the humans detected, you have the temporal outline, so you want to really know at which moment in the video which human is performing which action, and can go even further and determine who is the person performing the action. And so here, what are the different techniques which people are currently using? So what they do initially, they detected the actions frame by frame. So they just took a frame, applied known techniques for each frame. And so more recently, people have been looking at how to combine information from several frames, for example, by using joint models over several frames, or by using spatio-temporal 3D convolutional filters. That's kind of the state of the art, that people have extended the 2D convolutions to 3D. Once you have that detected on chunks or frames, the next step is to track the actions for the video. So you have to really see how these different chunks are combined to each other. And then something which is also important is to localize the action in time, right? So basically, once you have these tracks, you want to know at which moment the person is performing precisely which action. And then the first thing, which I mentioned before, was the importance, obviously, of data sets. If not for training, then at least for evaluation. And so standard data sets for action recognition, they just had these very simple sports actions where people are just performing one sports action. It's super easy. And so what we have done here is we have created a data set where people are performing different actions. So every human in the video is annotated, and the annotations can be several actions. So here, for example, the woman on the left, you have the action sit, talk, watch annotated, so you don't have only one action, but you makes it even more complicated because you can have here multiple labels, right? Because you're never only performing one action, but you're performing multiple actions by definition, right? You're sitting here, you're listening to a talk, and maybe you're watching something on your iPhone or something which you should not be doing. So basically, that's something you want to detect simultaneously. And so here, it's important to have these large data sets for evaluation and also to see what are the limitations of current methods. And so one limitation which we observed was that if you just have these 3D convolutional filters in space-time, you don't model the object which you're interacting with, right? So here, for example, you think this is a response, or this is a response for handshaking, but basically you don't have a model, you don't model what the interaction with the other person is. So you reach out the arm, but you don't know that the other person is not shaking your hand. The second example, similarly, is a false answer for smoke. And again, the person is holding his mouth, but there's no cigarette. So basically, again, you would need to have a more precise description of the action where you model not only the interaction, but you also model the object the person is interacting with. Third example, similarly. And so here, we have gone to two recent approaches. The first one is actually a structured model. So here you want to go away from just modeling individual features or descriptors. What you want to do is to create models which take into account how the person action evolves over time and how it interacts with the environment. And so here what we have is we have first actor tubelets. So it's again something where you link the actors over time. And what's important here, instead of just averaging the information over these tubelets, you use graph convolutional networks to model how these features evolve over time, right? And so what it really does, it gives you a predictive model over how these features interact together. So for example, if somebody is sitting down, you have different sequences than if you're standing up. And so here what you do, you first model these sequences of actions, and then the second thing which we have here is you have these object proposals. So object proposals give you other human regions and other objects in the image. It's not necessarily labeled, but it's weakly supervised, and then basically what you learn here in a weakly supervised way is which of the objects are relevant for the action. So you simultaneously learn how to model how things evolve over time and which objects are important for the action. And so here, just what I said before, you have this temporal dependency models and the relational modeling. And so here you can actually see an example. So on the left, the action is recognized as sit down because what you just see is the information in the middle frame. And then on the right, you can see the results with our model, and you actually model correctly fall down because you don't just average the features over the track, but you see how these different features evolve over time. So you can see basically in the beginning, the girl stands and then falls down, while if you just take the average of the features, you think that she's sitting. And the second thing is this modeling of spatial relations. So if you just have the model here on the left, you think that the guy is holding the fork, while here, if you learn this graph, you can actually see that the fork gets a high response. Basically, it's for eating, right? So you can learn in a weak supervised way that all the people who are eating hold some kind of object, fork or a knife, and then basically here you can see that the soft relational graph, you get the highest response for the fork. And then another example for action recognition is basically what you would want to do, not only recognize the actions, but you also want to predict what's going to happen in the future, right? So basically here, should you wait to see if the person is going over the street and hear what is happening to the child? Is the child falling down or not? And so basically what you want, so predict the next action. So there's action prediction. Here they're sitting and talking, and the next action would be clinking glasses. So that's kind of what you would want to predict. And basically, what kind of information do you want to take as input here? You have the human in the appearance and its dynamics, and you want to see, given this dynamics, what's likely outcomes, right? So you cannot predict with 100% certainty that there will be clinking glasses, but basically if you look at this thing, it's quite likely that there will be clinking glasses or not doing anything, right? So basically you have these different options, and what's nice here is actually that you go away from the very detailed models which just have spatial prediction of pixels. You really understand what's going on and use this understanding of what's going on to predict the future actions. And so here, the model, basically what the model we're having, so basically what you have here is you have the past, the present, and the future. You have the past and the present, and what you want to predict is the future, right? So for example, here she's riding horse, then she's riding horse and talking, and then basically the next thing, because the guy is holding the horse, is that she's getting off the horse, right? And so what's the model we're using here? The model we're using here is that we first have our action proposals and our I3D descriptors, but then on top of this, we have a spatial-temporal reasoning model which reasons how the different objects in the image interact with each other, and then a recurrency which models how the different objects evolve over time. And so these two components together are modeled by graph neural network and a GRU on top of it. So GRU is one of the recurrent models. And as nodes, we have these region proposals, and then we can learn the edges via attention. And this way, we can show that we can actually predict better models of the future. And if you look here, a few examples. So here on the top, okay, it's a bit hard to see. On the top, you can see that the guy sits and basically forecasts eating. And if you look at the image on the right, you can see that the guy is actually eating, right? And here, you just see this image here, and the forecast would be getting up. So this is what the guy is actually doing. He's getting up. So this is basically not seen when you predict the action, and then you can look and you see that the result is correct. Okay, and then if you look at some of the, okay, I don't have it here, but if you look at some of the incorrect results, sometimes basically you would forecast getting up, but then he just sits. That's basically what's nice here. You can have some probabilities of what's going on, right? So you can say 2 actions are equally likely, so you don't have to make a hard commitment, but you can kind of predict that 2 of the actions are likely, and then you can see what's going on in the future. Okay, and then the last part here is the interaction with the real world. So as I said before, now that we have techniques for object detection which work well, what we would want to do is to learn actually how a robot interacts with the world. And so the techniques which we have developed, so we've been looking at different reinforcement learning techniques, and the latest technique which we have developed is a combination of imitation learning and reinforcement learning. So why did we do this? Because if you only have reinforcement learning, you cannot learn the whole state space. And so basically, if you have skills which are learned by imitation, you actually have a much better grasp on the problem. And an alternative which people are now developing is model-based RL. And so here, what we have is we have this hierarchical RL with BC skills. So here you can see a set of different skills. And what's actually nice, if you look here, is that basically, if the action is really hard, you can see is that if you just take the skills ordered as they come, the results are much lower than if you put RL on top of it, right? And so here what you have is you have the primitives go to the red cup, go to the green cup, pick up the cup, go to the bowl, pour a cup from a cup, pour to the free space. And so this is all for now in simulation. And then the next question was, how can we get this working on a real robot? And so basically what's actually quite nice is if the robot is precise in simulation, you can actually do the transfer from sim to real only on the visual data. And so here you can see that it actually runs very nicely on the real robot. And so the mechanism we used for doing the sim to real transfer was by learning how to do data augmentation. So basically what we use as input here is a depth image. So you take the depth image, you can see that it's actually much more noisy in the real world than what you would have in simulation. But by augmenting okay, you just see the failure cases. So here the failure case is basically you cheat to trick the robot, and he still manages to kind of follow but it kind of fails in the end. And the second failure case is a glass which is transparent, and that's something also the robot fails. You can see actually it kind of generalizes quite nicely. And so here the objects which it sees are different from the ones it was trained on. And so the way we're doing sim to real transfer, so we found that the robot geometry is precise enough that we don't have to retrain it. It can be ported directly from simulation to the real robot. And then for the vision, you can see that the vision is quite noisy. And so here the data augmentation is done in a way that you have one data point which is real, so you know the position of the cube in the real world, and you want to use the synthetic data. You want to augment the synthetic data so that it kind of predicts the position correctly. And the augmentation is done in a way that you have a whole set of transformations, and you do, by greedy search, you determine which are the transformations which you should apply, which are most relevant. It's actually quite nice then that with this sim to real transfer, you can then have it run on the real robot. And so what we found very recently is basically for grasping, it works very well, but then if you want to go to more complicated actions, such as pouring or doing manipulation of multiple objects, you probably need to refine further your visual input. So right now we just have a visual input, which is a whole image, and that's what people do nowadays, but what would be interesting is to go to more object-centric inputs to your robot. Okay, I have 1 minute left. So basically, in conclusion, we've seen that one of the things which are currently missing is to develop models, more sophisticated models, which take into account the spatial and temporal information. So basically, people have looked recently at graph convolution and recurrent models to see how you can take this information into account. And what we found there, it's very important that you have enough training data. So basically, if the training data is too small, you cannot really model this very precisely. We've shown that we get very good results for weak supervision. Things we're looking at is self-supervised learning, where you combine jointly videos and speech and text. So basically, the idea would be to not have to model these things explicitly, but just take the combination of video and speech and text as input and be able to train features from there. And then one thing which is maybe quite obvious, but still it's very important that the input to your weak supervised systems, such as human detection or video object detection, are of high quality, right? Because if the less false responses you have, the easier your weak supervised approach gets. And then the last point, so cross-modal integration with text and sound, I said before, that kind of joins the self-supervised learning. And then the last thing which I'm currently starting to look at is this interaction with the real world. And basically there are two things which are important or interesting is basically how do the techniques which we have seen from computer vision generalize to this problem. And the next step, which I'm hoping for, is that you can actually learn this to learn better feature representations, right? So if you manipulate objects in the real world, you can really hope to learn better representations. Okay, thank you for your attention.